Great. So hello and welcome everyone to today's WFO webinar. My name is Gunnar Herzig. I'm the Managing Director of the World Forum Offshore Wind, and it's my great pleasure to welcome all of you to today's webinar on lightning strike impact on offshore wind, detection, loss mitigation, and insurability. And it's also my great pleasure to welcome our three excellent speakers today, Ralf Skowronnek and Barbora Bechnak, both co-founders of Skowronnek Bechnak, and then Marjan Valand, Business Development Manager Renewables at DEHN. And let me provide you with a bit of background on our speakers. So Skowronnek and Bechnak are well known in the offshore wind insurance world with offices in Hamburg and Tokyo. They're also very active in WFO's floating offshore wind committee, seeking for solutions to achieve risk mitigation, cost reductions, and insurability of new floating offshore wind technologies. And the company DEHN from Bavaria, Germany, is a world leader in lightning strike and overvoltage protection with 120 years of experience and more than 1,000 patented innovations and products. Today, both companies together will show us how it is possible to get future lightning strike damage to wind turbines under control and how to make it insurable. So great panel today. Thank you very much to our three speakers. And before we jump into the discussion, let me just tell you a few things about WFO and our organization, who we are, in case you're not familiar with WFO. So we are a non-profit organization founded in 2018. Our members represent the complete offshore wind value chain, and we have an international setup with offices in Hamburg and Singapore. And with regards to our activities, it's actually very straightforward. We do three things. We lobby for offshore wind and advocate for offshore wind around the world by talking to governments and regulatory bodies. We inform about offshore wind via all our media channels, conferences, webinars, and databases. And we connect the global offshore wind community via events and committees such as our floating offshore wind committee. And in terms of members and who our members are, you can see on the next slide that we have a very wide range of companies and organizations from around the world. And if you're not a member of WFO yet, please make sure to join us. Feel free to check out our website. And if you have any questions, please feel free to contact me directly. And then we would be more than happy to also welcome you as one of our more than 60 WFO members. So I think that's it from my side for the introduction, and it's now my great pleasure to hand it over to Ralf Skowronnek to introduce the presentation. So without any further ado, Ralf, over to you.
So thank you very much to everyone, and good morning, good afternoon, good evening, wherever you are. Thank you very much for giving us the opportunity to have the possibility to present something as a topic which is something which we find very important to discuss, because it's one of the major risks which is coming up for offshore with respect to offshore wind in the future. Next to earthquake and typhoon and other new technology risk, lightning strike is really something which in the next generation of offshore wind farms will have to be discussed and will have to be mitigated. So just very shortly about us and our company, because this is not the major topic today. The major topic will be definitely Marjan from company DEHN with the lightning strike mitigation systems. So Skowronnek Bechnak is a company founded 2 years ago with locations in offices in Hamburg and Tokyo. We are working as lenders insurance advisors, as project insurance advisors, and also as cooperation partners for insurance brokers. In France, for example, we are working with Cabinet BC on floating offshore wind, and in the World Forum Offshore Wind, my responsibility is to be the chairman of the subcommittee insurance of the floating offshore wind committee. And I also welcome some of my old colleagues from company insurance broker Marsh, where I was head of offshore wind and head of renewable energy continental Europe. In my former career. So a very warm welcome also to you. And together with my partner Barbora Bechnak, we are co-founder of Skowronnek Bechnak Japan Kabushiki Kaisha. Barbara was also working with Marshall McLennan before, and she was head of renewable energy for continental Eastern Europe and CIS. And we both together, we are working on risks from coming from two sides. So Barbara is coming from the insurance legal advisor side, so the legal perspective, contract perspective, and I'm the insurance engineer coming from the technical side. And we are always working on projects where we have some new challenges to overcome or some technical contractual risk difficulties to manage. Just some three examples. Barbara has already experienced with as an insurance advisor on the Taiwan offshore wind projects, and especially seen, let's say that there are already some difficulties in purchase of coverage against natural catastrophe. We are not talking about lightning strike yet. It was already when it came to the other natural catastrophe coverages. Then we worked as a lender's insurance advisor on a German offshore wind project where during the construction work, the WTG manufacturer went insolvent. It was a very complicated project, but with the whole team of advisors and the broker on the client side and the client and us as lender's insurance advisor, we were able to manage this. And we are also working on a project in German offshore wind with the third turbine supplier, so with a new turbine technology, where we are now in under contract for the last 2 years. And the major interest should be, and where we are going into a deeper dive, is into floating offshore wind, where I'm the chairman of the subcommittee insurance of floating offshore wind. And in cooperation with Cabinet Bessé in France, we are working on les éoliennes flottantes du Golfe de Lion, EFGL, and where we are, yes, trying also to help the industry together to get the new risks which are coming up as difference to bottom fixed offshore wind, which especially are the floaters, the mooring systems, and the cables and the turbine motion behavior on the floaters to make it better insurable. And if we add this now with the additional risks which are now coming up when we are now going into offshore wind in Asia, then in Asia there are three another risks which are coming up, additional risks which are not in the focus in Europe yet, which are earthquake, typhoon, and lightning strike. And this is the reason why we have decided definitely to have a deeper dive into the lightning strike issue. And Barbara will start now to explain from a contractual perspective where we are coming from, and to give you an overview about insurability and about risk allocation, and why it is so important now to prepare for it. And then Marjan, Valand will provide you with a real great presentation about the technical background and how to equip turbines with modern lightning strike measurement systems. Because, and this was also unknown for me, lightning strike now can be really quite accurately measured. So we have some really new perspectives now for the future, how to equip our turbines. So I hand over to Barbara then. Thank you very much.
Yes, thank you very much, Ralf, for the introduction, and also to Gunnar for giving us the forum to present this very relevant topic. So as Ralf has mentioned, we are acting as insurance advisors and we are assisting the parties negotiating the risk allocation. And we are also often engaged as lenders insurance advisors. And this means that on behalf of lenders, we have to check the adequacy of insurance coverage for projects that they consider financing. And because these are generally long-term financing projects, we are not only concerned about an adequate insurance coverage during the operation, during the construction phase, but also during the entire operational life of the project, and in case of project finance, at least until the full and final debt repayment. And this leads us to the question that the insurance that we are checking and confirming to the party that is available should be, from our point of view, sustainable insurance, which means that it should be there when and as long as it is needed. And over the years, we have been really concerned about the risk of the lightning strike, because we have been confronted with the situation where contractually the risk of the lightning strike is defined as a force majeure, and this in very simple terms mean that this is a risk which is beyond the control of the parties and against which they cannot protect themselves. And additionally, in a number of contracts, we've seen that it went even further, in that the force majeure was also defined as the employer's risk. And this taken together in the offshore wind context very simply means that in case there would be a certain loss or damage suffered by the wind turbine, then the entire loss, and entire means both the physical loss and the business interruption and the lost production, would have to be borne entirely by the project owner. And we have certain difficulties with accepting this, but as I said, over the years, we've been confronted with the situation that this is perceived as a so-called standard risk allocation. And additionally, the wind turbine suppliers argued that the project owners have the possibility to insure against this risk. And from our perspective as insurance advisors, this is only partially true, because even though it is correct to state that there is generally the insurance available against the risk of the lightning strike, in case you are, as a project, experiencing frequent losses, the response from the insurers will be at the beginning, or as first, to increase the deductibles and also to increase the insurance premium, which means that you can be charged the double of what you were charged the last year. And if this should not remedy the situation, then insurers can even go further and refuse to cover this risk. And this means that they can completely cancel the insurance policy, which for us as insurance advisors is a very difficult situation, because we can no longer speak about sustainable insurance. And this was the question that was really concerning us over the years. And we were trying to find a kind of solution, but we have realized that it's very difficult in the absence of a technical solution, because contractually, when we try to really see why is it defined this way, we have seen in a number of contracts that the risk of the lightning strike was defined as a risk which cannot be measured. So it was perceived as legitimate that the wind turbine suppliers should be able to disclaim liability for this risk. And we were not really able to move further contractually until last year, where we assisted at a very interesting presentation by Marjan, which you will also shortly see in a slightly modified form. And in this presentation, we heard that it is actually possible to very accurately measure the risk of the lightning strike. And this is both in terms of a single hit, so per lightning strike, and in the aggregate, so the accumulated charge which the wind turbine has received. And having heard that there is a technical solution to this problem, we thought that it should enable us to revisit or revise the contractual allocation, in that the entire risk would not have to be borne fully by the project owner, but it could be shared between the turbine manufacturer and the owner. And this brought us to the idea that if we are able to share the risk, then this should unburden the insurance, and of course over the years should bring it back to sustainable insurance. And I will stop now and will give the word over to Marjan to make his great presentation. following which Ralf will present our conclusions and recommendations to help projects achieve the sustainable insurability for the risk of the lightning strike.
So, okay. Okay. Oops. What's this now?
Just go to full screen, Marjan, then we're all set. Yeah, perfect. That looks great.
Okay. It's working. Yeah, greetings to everybody. So my name is Marjan Valand. I am now working at company DEHN for more than 2 years as a business development manager for wind and photovoltaic solutions. I worked in this industry, lightning and surge protection, now for almost 6 years. And I've been involved in wind already from the almost very beginning, because at the end of the university, my diploma was about pitch control, so developing a pitch control for a wind turbine. So this was now already about 20 years ago. Okay, so let's start with the presentation. First, a little bit about our company. So DEHN is a company that is already 110 years on the market, and during this time we presented a lot of innovations. So we were always the first ones to bring new solutions, new products to the market. And we are present now in 70 countries. And due to having not only the products for the lightning protection, but we have also services and design solutions. So we really cover everything associated with lightning protection. We also consider ourselves as a market leader. And we have around 2,000 employees, 1,100 are approximately in Germany, the rest is worldwide. And the company makes around 300 million euros turnover. We also acquired quite some years ago the strongest lightning generator that is available for civil use for the R&D. So it's able to generate 400,000 amperes. We see it here on this picture. And we do a lot of testing here also for the wind industry. So you see here one section of the blade here down on this picture. So this blade will be then subjected to different kind of tests in order that the manufacturer can then also certify this blade according to IEC standards. We are involved in many industries. Of course, wind turbine is one of them, and at the moment it has quite a focus. And as we see also here on this picture, so we see here offshore wind turbine park, and then onshore wind farm. As also we see, there are some lightnings behind. They are very near to these wind turbines. This also gives you already some indication that the wind turbines, being tall objects, of course also other objects have the similar characteristics, but due to being tall, they actually attract lightning strikes a lot. So actually there are many lightning strikes happening across the wind turbines, but the operators and the owners simply don't know it. Because until recently there were no useful lightning measurement systems. The ones that are now are able to measure, but not everything completely. Little bit about background for our lightning measurement system, how we started. So because we are making complete lightning protection designs for various objects, among them are also tall objects like wind turbines, radio towers, high buildings. So we already faced and we already saw that these kind of objects, they attract or generate a special kind of lightning strikes. They trigger actually special kind of lightning strikes. So we noticed and we realized that this has to be investigated, because also in wind industry we were aware that lightning measurement systems will be most likely needed soon. So during our daily job, so we also saw and were able also to analyze a special kind of lightning strikes. As we see here, this is actually an upward lightning strikes, and it's a fact that the tall objects like wind turbines, here on the picture we have one tower on the hill, but actually the wind turbines even more so, they actually trigger upward lightning strikes, so from the wind turbine upward into the cloud. So this is contrary to intuition, where we all know that in nature the lightning actually, what we also can see, lightning would come from the cloud down to the ground. But these are natural events. Here, this on man-made projects, actually it happens in the other direction. Very often, not always, but very often. So we knew that we have to investigate this. So we started our study that was initiated, lasted for around 10 years. And during this study, we learned a lot about various types of lightning strikes that are happening over the wind turbines. So the study actually revealed that there is a quite big difference between two types of lightning strikes. So the first one is this very classical lightning strike, so from the cloud down to the ground. So this is, we call it impulse lightning. It has a very high amplitude, very high electric current is released, is flowing actually from the cloud down to the object, in this case to the wind turbine, but it is lasting for a very short time. We talk here about microseconds, not milliseconds, but microseconds. And this event actually is defined by its peak amplitude. So usually this peak amplitude can reach even 200 kiloamps. So probably many of you already heard in discussions with the manufacturer that manufacturer would say, my wind turbine is built according to lightning protection level 1, or my wind turbine can handle 200 kiloamps. So this means that the lightning protection system in the wind turbine was designed and tested so that it can handle this kind of lightning event. But we realized that this kind of lightning event actually doesn't happen so often on the wind turbines. And also compared to the other types, which are actually from the wind turbine upward in the cloud, so upward lightning strikes, which we call as ICC types, that this impulse lightning strike is not happening so often. Only around 10% of all lightnings would be such kind. The rest is actually an upward lightning strike, so ICC, which I will talk also a little bit more further. And then the study revealed also that very opposite to this impulse lightning strike, there are very special lightning strikes. So ICC only, we call them ICC only, and ICC means initial continuous current, because they are starting slowly in comparison to the impulse lightning, and then they are rise to a certain level of the electric current, which is not so high, maybe only a few hundred amps, and this lasts then for a quite long time. It can be even up to 1 second. So here we are talking about yeah, more than 1,000 times, a few thousand times longer time duration of this event. But still, this event is defined actually by electric charge. You can think of the electric charge as the energy. There is a direct connection between the charge and the energy. If we look the charge, which is actually the area below this curve, so the gray area, then we see that the Icc Only Event actually has a bigger surface as the impulse lightning strike. That means that this kind of events, even though they have much lower electric current, they still can have a larger amount of charge or energy, and they are not easy to detect due to the fact that the electric current is so low, actually, so below 1 kilo ampere usually, and it's always it's difficult to measure them because you still have to measure this very high impulse lightning events where the current is very high, but the duration is very short. Okay, so here shortly we want to show you the effect of one very typical Icc Only event, which was actually generated in or simulated in our laboratory. You will see here we initiated on the one sheet of the metal below. So above is a small ball which is releasing the lightning strike. So we see the plasma channel now is jumping around. So this is completely the same as it happens with the real lightning strike. And this plasma channel actually has a heat of about 30,000 degrees. That's why what actually happens, so the result you can see here. So on this metal sheet, there are 4 holes. So this lightning event actually managed to puncture this metal sheet on 4 spots. And it was so-called Icc Only Event. So we see here, okay, it started slowly, then for the whole duration, the amplitude, the electric current was pretty much the same. It was very low, actually, only 400 amps, which is nothing compared to 200,000 amperes. But it lasted for a long time, half a second. This meant that this event released around 200 coulombs of the charge. And this is also the value very near to the ones that the blades are certified for. But just to give you the example that this is actually this kind of events, they happen very frequently. They happen around 50% of the time across the blades of the wind turbine. And actually next week we are doing another test, so where we will then use the real receptors and we will subject them to much more extensive testing. And then we can then also share the results and the pictures then later on. Now we need to also look a little bit in details the shape of this Icc type of the lightning strikes. And from there we will see that why is accuracy to measure accurately also very low electric current of the lightning strike so important. So here this is one shape that we took out of the IEC standard for the lightning protection for wind turbines. So we see here that there is one area, a blue one, which covers mostly just the spikes. So so we see here the curve of the lightning current. It has this initial continuous current component, but still there are some spikes. And these spikes, they are not difficult to detect. There are many devices actually which can do that, but as we see already here, the spikes by themselves, they don't represent a lot of charge or energy. So actually, most of the energy that is then released and that the lightning strike has is actually this Icc only Icc type of the lightning strike has is actually below this threshold of 1 kiloampere, and this actually represents 80% of the lightning energy. So that's why it is very important that the lightning measurement systems is able to measure this current, this quite low current, because most of the energy is hidden actually here, so below 1 kiloamp, and many times the value of the current is even below 100 amps, and this is not that easy to measure. So there are actually there are just a few systems that are able to measure in this range, so below 1 kiloamp, but they have difficulties to measure this range accurately. On the other hand, our system then detects, which you will see a little bit later, is able to measure also very accurately also this range here. So where the most of the energy is hidden, and this is anyway this Icc type of the lightning strikes is lightning that happens most frequently. So 90% of lightning strikes will be such, 10% will be this classical impulse lightning strikes, and among all these lightning strikes, 50% will be Icc only. And if the operator does not get reliable information about electric current, so below this threshold range of 1 kiloamp, he can really not make any good decisions, because maybe he doesn't make any decision at all, because he gets information that there was a very small lightning strike in terms of charge or energy, and then you can really then miss or you skip to detect small damages, which is very important, that but we will also see a little bit later on. I would just like to refer a little bit to the lightning protection standard for wind turbines 61400-24, and Japan has its own, so YES 1400-24, and the standard actually mentions what is actually the purpose of monitoring system. And so one of the important features of LMS is that it should help improve O&M activities. That means that if you're able to detect small damages, and by this you avoid bigger ones, so you have O&M activities which last for a much shorter time, and also the downtime of the wind turbine is then also much shorter. And the next function is also that you can improve a lot your risk assessment process. That means you now really gather valuable information and also realistic information. How many lightning strikes hit the blades? What was the energy? What was the charge of these lightning strikes? And then you see then consequently what kind of damage was created by this. So you can then estimate for the further years what kind of cost you will have, because the lightning strike density year to year doesn't change much. So of course there are some years where the intensity is bigger, but in any case, you have a lot of reliable information, and you can then do some forecasting, and you know what kind of costs you will have. But these two functions are only fulfilled if a lighting measurement system is able to measure Icc type of lightning strikes. And here, this includes also Icc only events, which are the most difficult to measure. So only in this case, you are then able to do what the standard also says that the lighting measurement system should really do. And let's look about the risk introduction and what is purpose in real life. So we have, for example, damage like this one, which was quite small, and this can be detected. So the lighting measurement system can see there was a certain lightning strike which could cause something like this. So you do the inspection, you find this damage, and you can repair it very quickly. If this is not detected, then this damage will expand, either due to just a natural environment and forces, or due to the fact that the lightning might hit also second time into this small damage. And then you are able then actually to prevent this big size damages, mid-size, or even catastrophic damages, because the size of the damage will just expand and grow. So here again, so high structures are very much exposed to the lightning strikes. Actually, they even influence the area, the location where the wind farm is installed. So before wind farm is installed, there is not that much lightning strikes in that area. After the wind farm is installed, you can expect around even 5 to 10 times higher lightning intensity of the lightning strikes. And again, the main goal is really to be able to detect small size damages, because you can repair them much quicker. They don't result in very big damages. And by doing this, you drive down the costs for maintenance, and also the insurance fees can be then also lower. And then let's see most common damages. So here we see the picture of the blade. We see here the receptors, also the main beams and the tip receptors. So these are the red ones. These are all items on the blade which are actually exposed to the lightning strike. And so very common is that the lightning will attach to the receptors. As we see here, this receptor already received a couple of lightning strikes, and it's already at the limit of its usability. So now it has to be replaced. If lightning hits even further, then these two holes which we see here in the middle, they serve that you can unscrew this receptor, and you can therefore replace it. If these holes disappear, melt away completely, you cannot replace it. But even more dangerous is that you have some cracks here around the receptor. So these are cracks in the glass fiber, and these cracks actually will only expand. They also contain some water. So if the lightning hits also next time, and the receptor is not any longer able to conduct the current very well, so it can heat up to the very high degrees, and then this means that the water surround will evaporate very quickly in a millisecond, and this can cause then already a small explosion. So therefore it is needed or very desired that you are able to replace the receptor at the right time. And then there is a next effect of the lightning strike. So it has also indirect influence. So the current will flow in the middle of the blade, and then even though these main beams, which are now these days from the carbon fiber, even though they are some, I don't know, 10, 20 centimeters away, still there will be some effect, and there can be some heating created by the lightning, and this heating can then cause delamination, and then delamination can then really destroy a blade completely. And this is also possible to detect. So first of all, you need accurate lightning measurement system, and then you need a very good model of the blade and to run some simulations. But it's possible to determine if a certain lightning strike also caused the heating of the carbon fiber, and there could be the problem of delamination. And this is also what we can do, our company can do. Sorry, this is the picture of the destroyed blade caused by the delamination. And now we have to look where are actually the areas where lightning measurement system is actually needed. So we see here the map of Europe, and we see here, if you look the area of the offshore wind farms, so here west, north, and then around UK, we see that there is not much lightning intensity. So this light blue means 0.4 to 0.8 lightning strikes per year. That means here we can expect in 2 years just 1 lightning strike per square kilometer per year. That is very low actually. And then the industry actually was very active, so many installations, they were gathering a lot of experience here. But now the wind farms are starting to be erected here around Japan, where we see here, and that in this area we have let's say this blue in the offshore region, where the lightning intensity is around 16 lightning strikes per square kilometer per year. So much more than what we see here in Europe. And the mainland anyway has a much higher lightning intensity. But this is not all to consider, because we need to look also where are the areas of the winter lightning strikes. And again, if we see Europe, so this green one, so that means that during the winter there is some possibility for the lightning strikes, and these strikes have then low intensity. But if we look this Japan, so we see here the red is actually covering all these regions, so near the coast and a little bit onto the sea. This is the most heavy lightning region where also during the winter time there are quite many lightning strikes, and they are also very heavy. So here the intensity is very high. So that means when it strikes, a lot of energy is released already in the single strike. And here on the land, there are already some wind farms, and as far as we heard, so already here now, they have quite many problems with lightning damages on the blades. And now these farms will be erected soon, also here offshore, where the wind turbines will still be in this region of very high winter lightning strike intensity. And then I would like to share with you one very interesting example from Ore Catapult. So this is from the wind farm around UK offshore, where after 5 years, when the warranty expired, they made a detailed inspection of the blades. They found 3 damages. I selected just this one, which I find most interesting. It was actually the smallest one among 3, but you see that not much is seen here. But when they cleaned it, they saw that actually also the balsa wood underneath was quite much damaged, already was rotting. And so they had to then clean it further. And so this resulted in this quite very big area, which had to be removed, and then the blade had to be repaired. But due to the fact that this wood was already rotting, that means that this damage was there already for a few months. It could be even for a few years. So that's problematic. And actually, yeah, the whole procedure to repair took 22 days. And if we look from our perspective, we are positive that if lighting measurement systems would be installed in such a wind turbine, and then this small damage would be detected immediately, then this repair would last quite much shorter, and there will also be no rotting of the wood. And here in this case, I must say they were very lucky, because if the lightning would hit second time into this area, and this moisture wood would heat immediately and then evaporate, and then you would have an explosion, then this would result in a quite bigger damage. And what is interesting, so we are seeing here one of the three damages actually in the area around UK, where, if you remember before from the maps, there is almost no lightning strike intensity. Okay, they were lucky, because this low lightning strike intensity also meant that maybe it would take another few years before the lightning would hit again into the same spot. But still, this damage was at the end not cheap. It was quite expensive to repair. Yes, and so let's look now our DEHN Detect system. So it consists of the main sensor is actually so-called Rogowski coil, and it's actually quite long. So we have different distances, and here I need shortly to explain why is it so long and much longer than what competitors have. So here is one from the competitor on the right, this small one. So when the lightning comes through the blade and then through the hub and then must enter into the nacelle, it's not necessarily that it will always go through a dedicated way, through the dedicated cable. It can split, it can travel elsewhere. And therefore, in order to really 100% to ensure that we measure the complete event, the whole current, the whole lightning current, so this coil is wrapped here around of all possible conductive parts, so that there is no way for lightning current to escape and that we would not measure it. So this is one. And the second reason for this bigger and longer coil is that we provide with this also very high accuracy for the low current range, where we are then also able to measure this difficult to detect Icc only lightning strike events. And then this is connected with some electronic devices. So data logger is a processing unit, also responsible for communication. And then we have blade detection units. These are actually small boxes that are installed in each blade. They give information which blade was hit and the timestamp. And the Rogowski coil, of course, then measures in detail the whole lightning event. But to know which blade was hit, so blade detection units are used. And yeah, we here have quite a flexible use, because our system supports 9 of such blade detection units. There are some blades where you have more than one down conductor, or you might want also to see if the lightning strike hit here behind, so you install also one blade detection unit here. And then there is also yeah, let's look now the video how the whole system works. So the lightning comes, it is then detected by the blade detection units, which says blade number 3 was struck at 1 o'clock afternoon today. Then it gives this information wirelessly. The lightning goes into a nacelle through the Rogowski coil when it is measured in great detail. and then everything is, the whole information is sent to the data logger, which then gives information further to the either to the local SCADA system of the wind turbine or to the out to the internet to the remote monitoring system. Okay, and now let's look versions. We have 2 versions. So this gives you flexibility because you can start with a simple version, basic version, where you only install the blade detection units, so without Rogowski coil. By this, you know then also very exactly how many lightning strikes hit the particular blade, and also the time you know, and also on average you also know what was the power, but just roughly. And when you see that, for example, certain parts of your wind turbine are much more affected by the lightning strikes, and this is actually also happening, then you can upgrade to a full version where you add the Rogowski coil just for this particular wind turbines, where you first already saw that this wind turbine is most exposed, or these turbines are most exposed. So this gives you this flexibility. You can start small and with less cost, and then you can upgrade to the full version. And there are few possibilities. This is also one unique feature from our system. So due to this length of the main sensor, Rogowski coil, you can place it also around the yaw system. In this case, you're able then also to measure if the lightning hit on the rear side, or where the atmospheric sensors are located, in addition to measuring the lightning that's coming through the blades. And there is also possibility to mount it at the bottom around the tower. And so the summary of advantages. So there is flexibility because you can start with the basic version, then you can easily upgrade to a full version. Then there is a very reliable detection because the lightning is detected first in the blades by the very simple blade detection units, and then also detected by the Rogowski coil, where it is also measured in details. And our sensor and the whole system actually is very accurate. So we have a very high precision of measurement for the whole range. So up to 250,000 amperes and down to just 50 amperes. And in this range, the error of measurement is very low compared to others, plus minus 5%. And there is also simple installation because the main part of the system is actually installed in the nacelle, so the Rogowski coil and the electronic devices. And the nacelle is much more easily accessible as the hub, because, for example, competitors, they would have the whole system here in the hub. And so we have only blade detection units here, which are small, so they are easy to be carried inside of the hub, and also they communicate wirelessly, so no hassling and trouble how to bring the communication through cables from the hub to the nacelle. So this is very easy for our system. And the system also has various communication options. So it can also communicate with the mobile network if it's available in the area, in addition to communicating with the local SCADA system of the wind turbine or with the internet, and to send to the remote monitoring systems all the information. And detailed evaluation then is possible through end customer own monitoring systems. And also for the pilot projects, we support this also with our own monitoring system, where the customer can then learn together with us how to interpret all the data that is collected. And So actually at the end, so let's look what are the benefits for the customer. So first of all, you get with such accurate lighting measurement system as DEHN Detect is, so you get really on-demand based rotor inspection possibility. So that means either if there is no lightning strike in a certain period of time and you are scheduled to do the inspection of the blade, you can do the inspection of the blade faster because you don't need to look in a great detail also for the lightning damages. You look then only for the, let's say, the front section of the blade of the leading edge, for example. But in case there were lightning strikes and such that they had energy and possibility to do the damage, in this case, you can then trigger immediately a drone, which then goes to inspect the blade to see what is the magnitude of the damage. So did the was only a receptor hit, what is mostly happening, and it's a little bit eroded, or is receptor already received so much charge that now it's already beyond his functionality. Or you can also trigger with such a lighting measurement systems, you can trigger also blade condition monitoring sensors or systems. So these systems are not able to detect lightning strike itself. They also would not be able to detect if damage afterwards is causing some additional vibrations. But if they are triggered and they know for a certain time, for exact time where they have to look if there was some additional vibration, then also this can serve as a very concrete detection of a damage that is immediately already affecting the blade. And then, of course, you get very detailed information about all lightning strikes, and also you can sort them just per a single thunderstorm, because it might happen that after the thunderstorms you had some damage and then you have to prove that there were certain lightning strikes. So below the levels which manufacturer stated that nothing should happen, and above all, so you have the ability to really detect small damages, which usually then would result in bigger ones subsequently. And by doing this, you also avoid subsequent, you avoid actually large maintenance interventions and also large downtimes. And yeah, we also know that if small damage is not detected and not treated soon or immediately, then it will definitely result in a bigger one. And then in the worst case, which is actually even not that rare, actually you come to the stage where you have to even replace the rotor blade. And this is definitely a big danger, especially for areas like around Japan, coastal area, where we have already very high lightning strike density, and we have at the same time also very high winter lightning strike intensity. And with this, this conclusion of my presentation, and I will give word back to Ralf.
I think your microphone is still muted, Ralf. If you unmute your microphone, that would be great.
Oh yes, sorry. So Marjan, thank you very much. This was a great presentation. And we just lost 3 participants, I can see. We had 60 and now we still have 57. So thank you very much for staying with us. And we now will just have a very short conclusion, because I think that the majority of you and of the audience here has already understood what can be done with this know-how in the own company. So regardless of working with an insurance company or with an insurance broker or with a project or with as insurance department of a company, asking the technical guys in the project if they did everything to mitigate the lightning strike risk. So in my opinion, this is a very important thing. Just another thing to consider. Because last year when we were sitting at the Munich conference and we heard Marjan for the first time having this presentation in March in Munich, we were asking ourselves immediately is this something new? Where does this come from? This must be a problem which has been already enough investigated. So why are we now talking about this? And more and more, when we were talking with him, we saw that, and he's not only talking for company DEHN as the expert, he's talking as an expert for this topic, that you really have to look into the details of the systems and the measurement as such, and the sensitivity of the system. So for us as independent insurance advisor, the main message is that regardless which system you are looking at in the future for your turbines, you should really have a deep dive into the detailed analysis of the system and the sensitivity. Just a short conclusion. In our opinion, these lightning strikes will have a significant influence on the levelized cost of energy. And I have added a number which is already higher than the official numbers in Japan on the maps. You remember Marjan said something around 20, but these are the official numbers already measured by the official measurement system. So if you're following his argumentation that the number of unknown or unmeasured lightning strikes, these Icc only events, which I find very impressive, were very, very small and low ampere, but very long lightning strikes, which you cannot see, are treating rotor blades like a welding machine. You can really say that the lightning strike in Asia can be up to 100 times higher than in Europe, which would mean that if you would take into consideration that an offshore wind rotor blade exchange, including the blade and the downtime, costs around, yes, we have calculated this around $1.5 million per blade. And if you would know that every wind farm will lose between one to two blades per year, then I think you need not talk about the amortization for such a system. I don't know, Marjan, this would be just my question, just very shortly. How much would such a system cost per turbine?
Yeah, so the full version, which might have some variance due to the different types of the wind turbines, but the cost would be around 15,000 euros. And then some wind turbines are different in size, and then this requires a longer main sensor.
So coming from the amortization perspective, what I understand now, if you say 15,000, of course I have to equip my whole wind farm. So having a wind farm with, let's say, 30 big turbines, I would have an investment of 450,000 euros. So I would have an amortization with respect to the wind farm of 1 year, because I would have the amortization already by having avoided the first total loss of a blade, which we find very important to know, because it is, in our opinion, it's much more expensive to transfer the risk of lightning strike to the insurance, because to transfer the risk of lightning strike to insurance coverage is, in our opinion, without technical risk mitigation, is not sustainable, and it should not be done. because as we already saw in onshore wind in Asia, insurers have to increase deductibles and premium and eventually refuse to provide cover. And we were very often asking ourselves, how can we treat such a thing? And also, I'm working now for more than 20 years in the wind energy business. I was always thinking that, okay, we are all treating this as force majeure in the contracts because it is not measurable. It is something which occurs occasionally, and now we see that it can be very accurately measured. And then following your advice, Marjan, what we did, we went deeper into the IEC 61400 and the JIS 1400, and there we see that the technicians in the business, and the experts, real experts in the business, they have already provided norms and certifications for this, where, for example, what we did not know in the JIS 1400, it is mentioned that after the lightning strike, the turbines have to be stopped immediately, which means such a lightning measurement system really helps to build up a real emergency response plan, an inspection and repair plan. So with the aim to reduce the downtimes of an offshore wind farm. So which means anyway, this has to be done in our opinion, since the risk still lies completely with the owner. So the minimum which has to be done in our opinion is to install these systems in these areas, so suitable systems, as you said, in these areas, and then definitely also to have the full care and responsibility for the whole emergency response plan, inspection and repair plan, cost calculation for inspection and repair, and maximum lead times, because the manufacturer is not responsible for the risk. So even if he provides you with a system where he's saying that it is in accordance with IEC 61424, the projects should care in their contracts that the employer's requirements especially are already including certain requirements to the O&M or the manufacturer, how and how fast he has to behave in case of such an event. Which finally leads to our conclusion, our own conclusion, that we think that in the future it will be possible to share the risk of lightning strike between the turbine supplier and the project also. So thank you very much once again, and with these words I'm handing over and going back to Gunnar. Thank you.
Perfect, excellent. Thank you very much, Ralf, Barbara, and Marjan, for your great presentations and for the excellent information provided. So very happy to open the Q&A session now. We have about 20 minutes for the Q&A session, and we've already received lots of questions via the chat function of the software system. If you have any other questions, just keep on typing in your questions, and we'll be more than happy to try to cover as many questions as possible. So the first very interesting question is around the comparison between offshore wind and onshore wind. So how have Asian onshore wind farms dealt with lightning strikes so far? Since lightning strikes also occur on land, the question is, has this already caused coverage to be withdrawn for onshore wind farms in Asia, or any deductibles increased for onshore wind farms? Any views or explanations on how onshore wind farms have dealt with lightning strikes so far?
May I answer, Marjan?
Yes.
Okay, so because it's something with insurance, so but definitely it's already, as you said, yes. Some onshore wind farms in Asia have already, they have already had a lot of problems with lightning strike damage to rotor blades, which already led to a typical behavior of the insurance company to really increase the premium year by year, and also increase the deductible year by year. And this problem already occurred, although it is onshore wind where at least a blade exchange can happen much more and much faster than in offshore wind. So this is exactly where we are coming from. So very good question, because we think that the problems now upcoming in offshore wind will be the larger ones than in onshore. I hope that this answers the question.
I would just add one thing. We cannot really blame insurers for this behavior, because if something is repeatedly occurring and nothing is done against it, then it is only really a natural response which has to be considered and also understood. That's our point of view to that.
I also I want to add something shortly. We also need to be aware that it will get even worse in the years to come, due to the fact that also the wind turbines onshore as well, they are getting bigger and bigger in order to decrease the cost. So you have also onshore wind turbines which where the tip of the blade reaches 200 meters or even above, and all the statistics or the damages that we were able to see now, this happened for the wind turbines where the height of the tip of the blade was below 200 meters, so 170 for example. And the higher the object, the more lightning strikes it will receive. So we will in the future see more lightning strikes hitting the wind turbines, the new taller wind turbines.
Perfect, great, thanks very much. And maybe next question, maybe for Marjan, since it's quite technical. So the question is, how is the blade detection unit installed during the blade manufacturing process, or actually later during the installation phase? That would be great. Any information about how the blade detection unit is installed?
Okay, the whole system or just the blade detection unit?
Okay, actually, this question is just the blade detection unit, but since the next question is about the Rogowski coil, so maybe you can just talk about the whole system, and if there are any differences between the components, feel free to elaborate on the different main components.
Yes. Yes, so it is actually very easy in both cases, either for installation during the wind turbine manufacturing or afterwards for the retrofitting. Due to the fact that most of the system is actually installed in the nacelle, where you have it's more easy accessible, you have more space, there you easily install the Rogowski coil, and you install also these additional electronic devices connected with the coil in a separate cabinet. So it's a very non-invasive procedure, so you don't connect with the important systems or interfere with important systems of the wind turbine. And the blade detection unit itself is a small box the size of a mobile phone. Of course, it is a little bit deeper than the mobile phone, but pretty much such a size. And this is just glued. There are some approved glues that you can use on the blades, and this is actually glued on top of the down conductor in the root of the blade. And also it's not heavy. The sensory blade detection unit is not heavy, so the glue will hold it tightly at the position. So there is also no danger that it will fall off. So I hope this answers the question. And also I must also add that if the installation is done afterwards, so retrofitting, it's quite easy for a person to come from the nacelle into the hub. Sometimes you have to go out, and then from the outside you enter the hub. So in this case, it's still not difficult because the blade detection units are small and not heavy. If any other system which you would have to use where you have to place the whole system in the hub, it's much more difficult.
Great, thank you. And yeah, maybe one more quite technical question, which is around how the information on the lightning strike is transmitted to the control room. And the person who asked the question wasn't quite sure if he'd understood it correctly, that it's transmitted via LTE standard, which the person then asks whether that is actually available offshore or whether that is not maybe too costly. Any information around how the data is transmitted from the offshore wind turbine to the control room, and whether it's correct that it's LTE standard or a different system?
Yes, I mean, this is only one of the three possible ways how to send the information out to the monitoring control room. So LTE is one of them, because it's also a little bit unique compared to other competitor systems. But of course, we still have a possibility where you connect directly through a cable to the local control system of the wind turbine, and then the wind turbine controller can receive all this information and then can send it then further, or you can connect through an Ethernet cable to internet router, which also can be inside of the wind turbine, and from there you send the data into internet to monitoring systems, and you can send it also in parallel, so to your own and also to our monitoring system. So it's using standardized communication protocol, and you can do it in three ways. So directly in the internet, directly into the wind turbine local communication system, or into the mobile network if you choose so.
Great, thank you very much. And then one interesting question again on regional differences of lightning strikes. So you've highlighted the difference between Europe and Japan, especially, but we have a question around how. So what about the US or other parts of Asia, Southeast Asia? Do you have any information on the kind of frequency of lightning strikes in those other regions, either other parts of Asia or China, Southeast Asia, or the US maybe?
Yes. Actually, we have maps, and quite a big piece of world is actually exposed to quite heavy lightning strikes density. So you have also very high lightning strike densities around Indonesia, then Malaysia, North Australia, for example, then Southeast China, then in India, Central Africa, very heavy. And what is interesting, in USA, south of USA, especially Texas, and then you have Latin America. I mean, there are many areas where you have even higher lightning strike density as in Japan, but the difference would be that other areas don't have that heavy, or they have almost no winter lightning strike intensity. So there are no winter lightning strikes on the other areas. But in general, like for example, we know areas in Texas, you have areas where you officially see 70 lightning strikes per square kilometer per year. That's official on the area where there are no wind turbines. Immediately when you build wind park, you place their wind turbines, you can expect with I don't know, 500 lightning strikes approximately per year per square kilometer. And usually in a square kilometer you would have 1 or 2 wind turbines. So this 1 or 2 wind turbines will will get or collect all of these lightning strikes. Of course, many of them will be quite small, but the damage is accumulative. So the receptors, even though they get a small lightning strike, they erode a little bit and then a little bit more and a little bit more. So it's important to know where is this level of charge that the receptor was certified for, because the manufacturers must do also certification for that. Once you know this, you immediately know that you are out of the safety region and you have to act, you have to do the inspection.
Excellent. Thanks very much, Marjan. And yeah, next question, it's actually very interesting and a bit challenging. So let me just read out the entire question. So as long as there is no obligation from the insurance market to install an LMS, why would owners invest in such a system? It will only be a further cost position that owners have to avoid. Yeah, any views on why to actually install this if it's not absolutely mandatory and required?
This is what we already mentioned. It depends really on the situation where the wind farm is located. I can understand, and this was already the opinion of a lot of clients during the last years, the last 10 years, 15 years, always. It's the same question. Now, when we are coming into regions with much higher intensity of lightning strike, we now come into another situation. It is the situation that due to the very, very high number of lightning strikes, now the projects simply can wait for the next 2 or 3 years until they are treated by the lightning strikes, and then start to consider their countermeasures, which will lead to the situation that during the next years, after the operation of the wind farm starts, insurers will increase premiums and reduce and increase deductibles after having had lightning strikes. But this will not help the projects, because because let's say the cost side on the project with respect to the high repair and replacement costs will be higher than to install such a system at an earlier stage. So this is the reason why we wanted to share this presentation of Marjan today with you, exactly to have the opportunity to discuss about exactly what's mentioned here in the question. So we can wait until this comes up as a future request of insurance companies, especially in affected areas where we have high lightning strike, and this is the reason why we wanted to share the presentation with you, for companies who are able to technically and financially calculate it, to give the opportunity to install such a system before. So this is exactly the reason for today's presentation.
I would like also to add shortly. If you remember, during my presentation, I showed one report from the ORE Catapult for one wind farm which is installed in extremely low lightning strike area. And even though there was a damage, and they discovered the damage, so after the warranty period expired, so the owner became responsible and he triggered the inspection, which then showed that there are 3 blades damaged by the lightning in area where there is almost no lightning strikes expected. And they had a quite huge cost because it was offshore. They couldn't work every day. There was some bad weather in between, so it took them 22 working days. I don't know exactly the cost, but I assume this was somewhere between 50 or 100,000 euros.
This is what I would like to add in addition. Thank you, Marjan, because in offshore wind, you not always need the request of the insurance company, because already the case which Marjan is explaining completely lies below the deductible of the insurance coverage. So this is project cost. So the typical offshore wind deductible is completely different to onshore wind. The typical offshore wind deductible has around 500,000 euros for property damage, and for business interruption always something between 2 and 3 months. So the scenario which Marjan is describing completely lies below the deductibles of the insurance companies. What we are talking about is, and why this could be serious in regions more exposed to lightning strikes in Asia, is the case that also in offshore wind, this could be insurance cases if the project starts to wait until not knowing that lightning strikes have occurred into the blade, and then we have the total loss, the necessary replacement of the blade. And imagine perhaps one blade per year or one blade in 2 years. This would be regularly an insurance loss plus full deductible loss to the project. So an exponentiation of 2 risks coming up. So of course, always the loss lying within the deductible. Offshore wind by the always have to be paid by the project, and the danger situation that probably the insurance cover might say in the next years that they will no longer prolong the insurance. So 2 risks coming up, which in our opinion can be mitigated by installing a sensitive lightning strike measurement system.
Great, thank you. And maybe, last question for today. It's a very concrete question around how the DEHN Detect product works in combination with insurability. So if a client installs the DEHN Detect LMS, does that mean insurers will not cover loss or damage if the minor damage initially identified is not repaired immediately? So any explanations you can give on what happens with the insurance mechanism once the DEHN Detect system has been installed, that would be great.
This is a typical questions we already had with the whole condition monitoring systems with gearboxes and generators and main bearings during the last 20 years. Clients always being afraid that by installing a condition monitoring system, they could be further exposed to exclusions coming from the insurance companies. This is really a very, very sensitive work which has to be done by the insurance broker, or could also be done by us when talking with insurance companies, because of course this has to be clarified. Clients should not be treated badly or not negatively if by installation of a sensitive lightning measurement systems, which is already also approved by the insurance company. This would be very important in my opinion, by exclusions of coverage. So this is exactly what has to be done, and what we the professionals during the last 20 years have also very, very positively been able to implement after the installation of condition monitoring systems for gearboxes, generators, and main bearings.
Perfect, excellent, thank you very much. So that brings us to the end of this webinar, exactly on time. So thank you very much again, Ralf, Barbara, and Marjan, for your excellent presentations. Great to learn more about this important topic. And let me just quickly point out to our audience our next upcoming webinar in June, which is going to be about floating wind supply chain challenges. So make sure to join us as well next month. And thanks again very much to the audience for joining us today, and to our 3 excellent speakers. Thanks very much again, and have a great rest of the day. Thank you very much. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye-bye.